Well, welcome to the 3D printing workshop. I'm glad that you all had the chance to make it out here today. To introduce myself, my name's Chris Haid. I'm COO of EnvyBots. We're located over on the other side of town, over in the Seaport District. And at EnvyBots, we focus on bringing 3D printing solutions to the educational space. Today, though, we're going to be focusing on how we can use 3D printing to gain some educational value. So, just to go over the agenda for today, I'll start off with how we can apply 3D printing in the classroom, a couple examples that have been used before, and a couple that we've developed, and a couple that teachers in my network have developed. After that, I'll be going through a quick overview of the 3D printing process, and after that, I'll actually introduce you to Tinkercad, which is very popular for 3D design, at least for introductory 3D design. It's a very great platform because it's cloud-based, it's free, and anybody with an internet browser and internet connection can use it. So I'll jump into it at this point. All right, so we'll start off with ways that we can apply 3D printing in the classroom today. So there are sort of at a high level, three main ways that we can use 3D printing to benefit our classrooms. One is to use existing lesson plans. So there are a couple ways to do this. One example is to go online, find different 3D printing projects that are actually available already, and afterwards I can go over a couple sources of these, but just quickly, there are quite a few databases of online 3D printed parts that many people have been building out at this point. Frog dissection kits are one that comes to mind, but there are numerous different projects that you can actually just get online or from other teachers that you may or may not know already, actually, that have been tried, true, and will print out for you the first time if you know what you're doing. The second way of doing it, instead of just taking somebody else's lesson plans, is to actually supplement your existing curriculum, taking advantage of 3D models that are available or something that you may develop yourself to fit in with an existing lesson plan. And final one, my favorite one, is spending a little bit of time to create your own 3D printing lesson plans, or I should say 3D printable lesson plans, because oftentimes the end goal of using the 3D printer in the classroom is not to teach 3D printing, but to use it as a tool to get to your end goal of educating. So I have a couple examples actually of each of these. We'll start off with how we can use existing lesson plans. So this is a prosthetic hand project that I actually developed over at EnvyBots, and this is actually designed in the Tinkercad software that we'll be covering today. We actually wrote out step-by-step instructions on how to get to this thing, and this is a project that can be done probably in just a few hours, so a couple class periods. And the great part about this project is that it teaches the students how to design, iterate through the design process, but also how to actually solve a real-world problem. How do you make something that can help a human being, somebody that doesn't have a hand or fingers, and how to actually be able to use your abilities to design, to make, to actually help somebody's life be a little bit better. If we move on, we can look at how we can supplement existing lesson plans. So this is another thing that we built out actually, are protein surface models that can be used in a classroom setting. So the great thing about these is these were all downloaded from an online database, the protein database, converted into the proper file type for 3D printing, and then 3D printed out. So these are great models because we can really illustrate actual concepts with them and use them to take education off of the textbook and put it into people's hands. So the last example is creating new lessons, and this is actually a lesson developed in Tinkercad by one of the teachers out in Fitchburg that uses our printer. So what she had her students do was design boxes in Tinkercad, which we'll be covering today, and actually have them challenged with making a box that would hold a certain amount of water and also have a certain surface area, and have the students design with that. And after they designed their box in Tinkercad, they, you can see they put their initials on it so that they could mark and see that it was their project. And also they had the opportunity to actually pour water into their box and see if it actually held the proper amount of water. So they got to experience design, learning about the third dimension, and then also test their assumptions in mathematics to actually see if they got what they were looking for at the end of the day. So this is a great project because it's something that was actually developed by teachers for teachers and is being shared at this point to really take advantage of 3D printing in the classroom and bring it to the next level in a very useful way. So, so those are sort of the three methods that we can use 3D printing in the classroom: supplementing our existing lessons, creating new lessons, and using existing lessons that are available. So at this point, move on, and next thing I want to cover is a quick overview of the 3D printing process, just to sort of give you a brief snapshot of it from a high level. So step one in the process is obtaining your digital 3D model. So what we want to do is actually get the STL file, which is just essentially the PDF of 3D files. So a 3D file that can be read by just about any program, is compatible with just about anything. And you can see here I actually got a model of chromatin fibers. This was off of the protein database, so that's where I got the file from. And I actually had to convert it to the STL file type so that we could work with it. But when you open it up in 3D rendering software, you can actually just see that that's exactly what you get. There's a structure of the 3D model right there, and the file will contain all the information that you need to give the printer for it to know what to do when it wants to 3D print this part for you. So to go into a little bit more detail on the STL file type, it's a very commonly used file for 3D printing. It was actually a file type that was invented for 3D printing back in the 70s. It actually describes the surface geometry of the part, so it doesn't tell you what's inside of it at all, but it'll tell you exactly what surfaces define that 3D model. And it actually stands for stereolithography, one of the first 3D printing methods, which it was designed for, but also is commonly known as a surface tessellation language. Sort of explains what the file type describes at the end of the day. As I mentioned before, I sort of think of the STL file type as the PDF of 3D printable files. It's a file type that any type of 3D design software out there is able to export. It's able to import that file type, so it's sort of the universal file type that anybody can use. So, moving on quickly, how are STL files created or obtained? So, one way to do it is to make the files yourself. The other method, as I mentioned before, which I had, how I got those protein models, is you can actually go to online databases and download pre-existing files that other people have either scanned, they've designed, have created themselves, and you can download those. A lot of the time they're freely available, so you can actually download those and use those for your own purposes as you need. So that's a quick overview of the STL file type, and that's sort of step one of the 3D printing process, is getting the 3D file that you want to get printed out. So step two is you need to upload your 3D file that you've obtained into the 3D printing software. So there's a number of different solutions out there. So at this point you can see that we have a picture of the chromatin fibers uploaded into the 3D printing software. And you might be able to see it better in your packet, but there's actually lines that represent the layers, because the way 3D printed parts are made is they're created layer by layer. So on this part, if you look closely, you can actually see that there are lines going up the whole thing, and those represent the layers. So that actually shows the path that the 3D printer takes to create this part for you. And moving on, our final step of the process is actually 3D printing your model. So at this point you can see we have a picture of the 3D printed model next to the original render, and you can see that there's actually a fair amount of, you can actually see all the detail that's involved in the part in the 3D printed model. So we can actually now hold the model and see it and use it for whatever purpose that we need from it, whether it's educational or just showing it off for fun. So at this point, move on to our next section. Now we're going to, I'm going to introduce you to Tinkercad, 3D design software that I use most often to educate new students, get people into 3D design, and have people take their sort of first steps in. So at this point, we'll move on to our laptops. So you can turn those on if you haven't already. And we'll start by going off to tinkercad.com. So when we get to Tinkercad, you'll find a screen that looks like this, and you'll go to the top right corner of the screen to create a new account. So now that we've created our Tinkercad account, we can actually go to our dashboard. So this is where you'll come to when you actually first sign in. And first step is to click on Create New Design. That blue button sort of right in the middle. And when you get to your new design, you'll actually find this window right here, and this is your work plane. This is sort of your working screen where everything is done. So there's a couple things I want to cover here. Great thing about this is it's meant to be very simple to use from the start. So the way they set it up is they give you a number of predefined shapes in the bar on the right side, and feel free to scroll down on in the bar on the right side. That's our objects panel right there. So you'll see that there are a number of different geometric shapes. We have cubes, cylinders, pyramids. If you scroll down, you'll find numbers, letters, and if you scroll down even more, you'll find a number of other parts that are user-generated and a couple of fun parts that they also added in there, I think just for fun for them. But sort of the first step, how we start off with this process, is you can click an object on the right side. Let's go with a cube for now. And you can actually drag and drop that into your work plane. Simple as that. So you actually have your first object created at that point. So if you look at that object while it's highlighted and you have it clicked, there's actually a couple features that you can do. And I actually have this in the slides, so you can use that as a reference. But these are the basic manipulations that you can do with any of the shapes in Tinkercad. So if you actually see there's a black arrow, if you zoom in, there's a black arrow on top of the object. That allows you to pick it up so you can move it in the z-axis, move it up and down off of the work plane. In the each corner on the base of the part, you'll actually see a little white dot, and if you click that, you can actually resize the part in X and Y. In the middle of that line, on that edge, you'll actually see a black dot, and that allows you to stretch the part in one dimension so that you're not doing it in X and Y, but just in Y or X independently. And in each of the corners, you'll see a little curved arrow, and that allows you to rotate the object, and you'll see three of those arrows that allows you to rotate in each axis. So it just gives you sort of the basic abilities to drag and drop objects, resize them, scale them as you need to, and rotate them and place them. And to move them around, it's as simple as clicking on the object and just dragging it to another location in the work plane. Something that's helpful, just to note, is in the bottom right corner of the screen, you'll see something that says Snap Grid with a number next to it. So you'll see by default it's at 1.0, so every time you move the object, it'll click to the next 1 millimeter. So if you set that, you can actually get that to be 0.1 millimeters, 1 millimeter, 5 millimeters, whatever the options are in there. So you can change that around to what your needs are. I usually just leave it at the defaults because that's close enough for most of my purposes, but that can be a helpful feature if you're trying to get things placed in the right location. So at this point, I'm actually going to shut down the PowerPoint and go into a guided tutorial on how to design our first part. And what we'll do today is how to design a house in Tinkercad, just to get you through the basic skills that you need. We'll go through just about everything that you need to do in Tinkercad to be proficient at it, and I'll let you guys take it from there. But today, my goal is to give you all the confidence to be able to bring this software back to your students and teach them how to use it to bring their own ideas to life. So I'm going to open up my own instance of Tinkercad at this point. So today what we're going to do is go through how to design a house in Tinkercad. So this will give you all the basic skills to use Tinkercad successfully. They include, as you'll see in your packet, how to place objects in X, Y, and Z, how to scale objects in X, Y, and Z, how to rotate objects, how to group objects, how to align objects together so that they're in the right place, and how to create holes or negative spaces in your objects. So if we go here, we'll start off with step one, which will be to sort of create the base of our house. So what I do for that is, am I in your way? All right, good. We'll take this box here and we'll drag it into our work plane. And I'll resize this so we can all see it a little bit better. One quick trick is that when you're dragging the corners to resize it, you can actually hold down Shift on your computer and then drag it, and it'll scale each of the 3 dimensions uniformly. So if you want to maintain your cube to be a cube, you can keep that geometry and scale up every dimension together. Just hold down Shift to do that. It's great when you don't want to scale each dimension individually. So we'll take our box right here, and that's how you scale it. And just to show you, what we can do is we can take each of the corners and we can scale them independently. So I can do that. I can take this corner and shrink the depth, and you can see I can also affect the width of the part. And we can also do this on each of the back corners. So we can grab that one and pull it forward towards us to scale in that direction. And same with the back right corner. Oop, missed it. Just like that. And if we want to make our box taller, we can also affect that by dragging this white dot that's in the top middle of our box, and you'll see the dimension will actually come up also, and this is in millimeters by standard. But if we drag this one, we can move it up and down and affect the height of our object just like that. So for now, we'll take this object that we just put in here and resized and move it off to the side. So next step for creating a house is that it will need a roof. So we'll need to put a roof on top of the house here. So what I'll typically do is grab this yellow pyramid that we have here, or the roof off to the right side of it. That's even more appropriate. We'll use that this time. And we'll drag and drop, oop, wrong one. Actually, I'll show you what happens when you get the wrong one. So I see I dragged this part in, but I don't actually want it anymore. All you have to do is have that selected, and then you can hit either backspace or delete, and it'll delete your part for you. So that's a quick way to undo that. Also, pressing Control-Z, the undo command, will also undo it for you. And additionally, we have in the top bar here an undo button in case we make mistakes, and a redo button in case we want to undo our undo. So in the top bar, you'll see undo and redo up there. But moving on, we'll drag our roof in here. Obviously, that's going to be a bit too small, so what we'll do is we'll try to roughly resize that so it's the same size as the box that we just made. And we'll also lift it up so it looks like it's about the right dimensions. Now, the next step that we'll have to take is actually taking this house that we have right here, or taking the roof that we have right here, and dropping it on top of the house, because that's where the roof belongs. So what we'll do is we'll grab this black arrow that points up above the top of the object and actually lift it up. And you can see the object will lift off of the work plane just like that. And at this point, we can drag the roof on top of the house. So you'll see things aren't quite yet exactly how we want them to be. The roof is a little bit misaligned. It's not the right size. But now that we have it in place, we can make it a little bit bigger, resize it so it's the proper size to fit the top of the house. And don't worry about getting these things perfectly aligned with each other, because we'll do that actually as the next step. I'll show you a good way of doing that. But once we see that the roof is about the same size as the house, and we'll fit on top of it, one important thing to do, and I'll actually illustrate this right now, is that you want to look at things from a couple different rotational angles. So from this angle, if we drop that down a little bit, this looks pretty close, like that could be a good looking house from this view. But if you go to the top left of the screen, you'll see a little circle with a house in the middle of it and a couple arrows. You can use that to rotate your object, to rotate the view of your object. So if you click the up arrow there, you'll see that you can see the top of the house. But if we rotate down, you can see why it's important to rotate our objects. these things aren't actually connected right now. And this is a problem. I'll go into more detail about this later, but this is a problem that I experience with just about every single one of my students when I introduce them to Tinkercad. So it's very important to emphasize that we look at the things that we create from different views to make sure that the 3D object that's represented on our screen is actually the object that we envision in our mind. So now that we're looking at it from this angle, we can drop down the roof so that it's at the proper height and contacting the house. Once we see that it's there, then we can actually take a look from a couple different angles and make sure that it's about right. But nobody really wants a house that's about right. So at this point, what we want to do is actually align the roof of the house with the house itself so it's centered on top of it. So what we can do is we can click the roof that we have right here and then hold down Shift and click the box that we have at the bottom. This will make it so that both of the objects are selected. Just like when you click multiple files on your computer in the File Explorer, you hold down Shift to select multiple ones. Works the same way here. So when you have both of those selected, and actually before I move on, there's another way to do this. You can actually, now that it's unselected, you can click here and drag a box around it, and that'll select everything in the box. So there's a couple of good ways to select multiple objects. But what we want to do now is if you go up to the top, right next to Undo and Redo, you'll see a drop-down menu called Adjust. So click that, and you'll see a feature called Align. So if you click that, now that we have both objects selected and we've selected the Align tool, you'll see a couple dots have appeared there. So what these allow you to do is actually align the part. And I'll get out of here so we can show it a little bit better. I'll misalign these so we can see exactly what's going on. But this tool allows you to line up things so that they're centered on each other. So if we click this middle dot right here, it will actually line up the two objects in that axis. And as you can probably guess, the next step is to line it up in the other direction. So we can click this other dot right here, and it will line it up in the x-axis. So now we have the roof perfectly centered on top of the base of the house. At this point, now that we want to proceed and we're happy with what we see here, you can go to the bottom and click on Dismiss Align Tool. And that'll get you out of that tool so we can proceed and go to the next step. So what I want to cover next is how to actually put holes into this. So every house needs a door. So I'll show you how to put a hole in the front of the house that'll look like a door. Also, another quick thing, as I mentioned before, to rotate objects, we can use these arrows up here, but you can also right-click and then drag to rotate to any view that you want. So you can see your object from any angle that you can set just by using your mouse or touchpad. Should also work with any touch screens that you use in case you have a laptop that has a touch screen, or if you're using an iPad or other tablet. So what we want to do now is create a door. So we'll drag in another box and move it right in there. We're going to want the door to be a little bit smaller so we can resize it so that it's about the size and shape of a doorway. So we'll take this object and we'll shrink it down a little bit. And you can see that's about the roughly the dimensions of a door right there, scaled down of course, about the right size and shape. Now what we can do is actually turn this door. Now it's a solid object, but we're going to want this to be a doorway that leads into the house. You'll see that there's a box in the top right that's called the inspector box. So what you can do with that is actually turn the objects that you drag and drop in from solid to negative space. So you can see in the top right, there's a button that says hole in there. So if we click on that, it will turn the object that we currently have selected into a hole rather than a part with actual mass and volume. So we can click that, and you can see when you do that your object turns see-through, like a ghost, that represents the fact that it is now a hole. So what we can do is drag and drop this box into our house, and now we've formed a hole in the doorway right there, and we've created a door for our house. All right, so at this point, now we have 3 objects all fitting together into one house that we have here. Sometimes if you click in the wrong place, you might accidentally knock an object off to the side, and then you have to redo the steps that you did before. That's never any fun, so I'll show you how to actually group these parts together so that when we click on part of it, it'll all move together as one cohesive unit. So, as we did before, let's select all of the objects by dragging and dropping a box around everything to select everything. And if you see right next to the Adjust drop-down menu at the top, there's an option to actually group all of the parts together that you have selected. So if you click on that button that says Group, you'll see the colors change, and the hole will actually look like a hole now. So you can zoom in on your object, take a look at it, rotate it a little bit, but you'll see when we actually rotate it around and move it around now, it moves as one cohesive unit because we've now grouped all of the objects together. So even if we rotate it, it all stays together at this point. So this is good if you have a part that you're putting together. Your end goal has a number of different shapes and objects that you've put together to create your final assembly. And if you're going through this process and you want to keep things grouped together, it helps to keep things organized when we group things together like this. So it's a great tool. It makes life a lot easier as you go through the design process. And as you design different things, you'll find how this can help you in different ways. So at this point, a couple more steps. So now that we have a house, we'll want to put windows on it. So I'll show you how we can put windows in by taking a block, lifting it up and turning it into a hole. And the last step that we'll want to take to complete our house is actually branding it with our initials so that we know that when it's 3D printed, we can find our part because it's labeled with our initials on it. So step 1, we'll start off with putting windows into the house. So you can take a box, yet again.
Is it a box hole or just a box shape?
Actually, that's a good point. We can do it with the box hole. So you can do it with the box hole or the box shape because in the top right there, you have the option to switch between the two. But if you want to directly bring in a box hole, you can actually scroll down on the right side. And if you go down far enough, there's a little drop down called holes right here. And if you click that, it'll give you a box hole and a cylinder hole. So we can drag and drop the box hole in. And you can see, yet again, it gives us the option in the top right to actually turn that into a solid object from a hole. So it doesn't really matter which one you bring in because you can switch the object from a box to a hole after it's in place. That's just there for convenience, but that's another way that you can bring in a box, or bring in a box hole. I'll hold down Shift. I'll shrink the size of my box. And that looks about the right size for a window. So now I'll move this over towards my house. We'll grab the black arrow on top of it to lift up the object to about window height. But at this point, we'll take the window and carefully just push it into the house so you can see the outline of it still, but also see that it's intersecting. So you won't be able to see the back of it anymore. So now that we have 2 windows, what we'll want to do is actually put our initials on the object. I found that this is important because especially when you have a printer printing out many different parts, especially our printer that you can queue multiple print jobs to, and you come in the next day and there's 30 parts in there, it can be tricky to sift through 30 houses and give the right house to the right student when it doesn't have a label on it and they all look very similar. If we were all printing out this one and everybody wanted to take their own part home, it would be very tricky to sort through all of them and get you the right part that you designed. especially if there's a large number of parts. So what we can do next is actually go to the Object Explorer on the right side and scroll down, and you'll find letters here. So what we can do is, just like with all the other objects, we can drag and drop these letters into place and put them where we want them to be. So at this point, what I'll do is I want to put my initials onto this object. So I'll drag in a C, my first initial for Chris, right into my work plane like that. But what we want is this object to be actually attached to the printed part, and right now it's just sitting next to it. So I want it to be facing out from the wall. So if I look at the side of this house, I can see that it says CH for Chris Hayde. That way I know that it's my part at the end of the day. So what we can do is we can zoom in on this part so we can manipulate it a little better. So we either use the scroll wheel, or you can click on this button here, Fit View to Selection, the cube that's right below the Rotate button in the top left. If we click that, we'll zoom in on our part, so we got it nice and full view for the thing that we're looking at right now that we want to rotate. And at this point, what I want to do is, you'll see there's this rotator bar right here. So I can actually rotate my letter in each axis as I need to. What I want to do is put this against the side of the house, so I'll rotate the letter in this direction so that it's facing upwards like that. And now what I can do is, you can see that the part is now sort of intersected by the work plane. Half of it's above the work plane and half is below. We'll want to lift up our object so that it's all above the work plane. And then what we can do is just carefully place it onto our structure, like that. And I now have the letter C branded into my house. And if I want to, just like before, I can turn this into a hole so that I don't have the letter C protruding from my house, but a cutout of the letter C cut into my house instead. So if you grab your letter, I'll grab H right now for my last name. If you get this slider, you'll see that depending on how far away from the object you are, it'll give you different fineness and control. So if you're close to the object, you'll see here it sort of clicks every 22.5 degrees is what I can do. But if I move my mouse further away from the object, I sort of move it into this outer rotator where I can actually affect it more finely. So I can choose it, and it steps by degree instead of every 22.5 degrees. So to do that, you click on that rotator and move your mouse a little further away from the object rather than close to the object, and it'll give you that finer control rather than the coarse control that you see when your mouse is close to the object and you're rotating it. So that's a nice little trick right there. Usually I like to keep my mouse close to the object because it's nice to be able to snap to, the closest 45 degrees or 90 degrees and get my object to be just at that angle. But if you need to have that finer tune control, that is an option just by having your mouse a little bit further away from the object. So as I did before with the letter C, I'll do with the letter H, and I'll lift it up so that it's all above the work plane. You can see in the bottom right of the part when I'm lifting it up, it'll actually give me the height that I'm at right now with the part. So right now I know that I have the letter H 1 millimeter off of my work plane. So that means I know that it is above the work plane. And then, just as I did with the letter H, I can move, just as I did with the letter C, I can move the letter H into the part so that it intersects. And again, I'll turn it into a hole so that it forms a cavity in my part. So now you can see we have the letters C and H branded into our part. All right, so at this point, what I like to do is, you can see my object's not really grouped together at all. So I just like to make sure as a last step that I have everything grouped. So I'll select everything, just dragging a drop box over the entire selection and hitting group. And now my object's all one color and grouped together, and I'm happy. So what we can do now is, what we want to do is rename our file from some silly nonsense name that it generates automatically into something that's a little bit more meaningful. So what we can do is go to Design and then go to Properties, click on that, and it'll bring up a window, and you can actually change the properties of this file. So it'll allow you to change the name, which I'll switch to House by Chris. And this is also where you can affect if the object is shareable or private. So if you want to, it was a question before I heard, if you want to share these parts with other people, whether it's with a teacher or another student in your class, anything like that, you can change the part from private to public here. And when you do that, anybody that looks it up can view that part. So downside is that anybody in the world can view it at that point, but also means you can share it. All right, so at this point, we have our object named with something a little bit more meaningful. We can hit Save Changes, so that'll save it. So at this point, what we want to do is, now that we've completed our house, we're happy with it, we've looked at it from every angle, we've made sure that everything's intersecting, that everything's together, our house is as we want it to be, labeled with our initials and everything. We want to do the last step, which is actually downloading it for 3D printing so that we can then send the file to the 3D printer. So if you go to the top left here, again in the Design tab, you'll go down and you'll notice that there's an option to download for 3D printing. And that is what we want to do. So if you click that one, it'll pop up a new window that gives you a couple different file types. Now these are different file types that are commonly used for 3D printing. As I mentioned before, the STL file type is the most common one. That's why they list that one first. So you can click that one. It will download your STL file of your house, which we can then send to the 3D printer. All right, so delving back into the slides. Next, what I want to go into is just quickly avoiding a couple of common pitfalls that a lot of people run into sort of the first times that we try 3D printing. So here's one that I mentioned a couple times as we were running through Tinkercad, and this is one that you want to actually look at in Tinkercad, is what happens when you rotate parts around. So you can see from the left side of this, we have a front view of the house. Looks like a house. It looks like the roof is on top of the house, sitting where it should. But we rotate around 90 degrees and look at the side, and everything is completely off. So that just illustrates why I always emphasize to my students that they need to rotate their objects around to make sure that things are snug together, that they're fit together, and that they're where they want them to be for actual printing. Typically what I'll do is I'll actually print one of these things and it prints out separately, and I'll hand the student the parts and show them, this is why I told you to look at your part from multiple views in the CAD software so that you got the thing that you want printed. I don't think that you wanted a block and a cube, I thought you wanted a house. And that's usually what they're going for, so usually I either explain that to them in software or print it out so they actually learn the lesson and have a physical object that shows what went wrong here. Next thing is things often things just about always print best when the base is actually flush to the build surface. So that work plane, that grid that you saw at the bottom when we were looking at 3D print preview, is actually represents the build plate of the 3D printer. Now things will stick best to the plate and will print out best when they're actually oriented just sort of in their natural orientation where it's sort of flush down to the bed. Again, the thing on the left will print, but it'll have a lot of extra support material, and it may not look exactly like you want it to. It'll have the right dimensions of the part, but it'll have a lot of extra support material that you didn't really need to spend the time breaking away if you printed it in the correct orientation. So that's another one that you'll want to avoid. So just like we asked before, will support material be generated? So you can see right there where we have that overhang, support material will be generated automatically if we leave that on the automatic setting, which I always recommend. I would say keep that on automatic unless you really know what you're doing and you have a really good reason to not have it on automatic, and you say, oh, it's hard to think of a very particular use case, but there may be cases where more advanced users would want to go down that route and say, I want material only below 87 degrees angles for overhangs. But typically I'll leave that to be automatic, And when you have features like that need support material, it'll automatically generate it there. And it may or may not generate support material over that door and within the windows. Here's an example of actually one of the models that I brought along with me. So that is actually this model right here. And you can see this is how it comes out at the end. So this was printed with support material in this orientation actually. And you can pass around and see after you break away the support material either with your hands or with a pair of pliers to get it off, you can actually get the your end product is very close to what it would be without support material. So you can see here we have the part sort of printed up, but we have these pillars supporting it. So the way the printer works is it leaves a small air gap between the support material and the part so that it's almost like a perforation, so it should break away easily. That's how it's designed to work. Sort of the common pitfalls in 3D printing and sort of what you want to be considering as you're going through the process. There's honestly not too much to consider because it's a process that's a lot easier to get from A to Z than you would with any conventional manufacturing methods. So for example, if you tried to mill a part like this or use a lathe in a machine shop, those are a lot more complicated methods, and 3D printing is a great way to get the geometry that you want without having to learn more heavy-duty CAM software where you have to choose tool heads and tool paths. This is a lot more automatic and a lot easier to use and a lot safer at the end of the day because it's completely hands-off. So at this point, I just want to go over a couple classroom examples that I actually brought along with me today. I'm sure a lot of you have seen them so far. But these are actually examples of the curriculum that we've been developing over at EnvyBots. So I have a couple models of proteins, and these were actually taken from the protein database, which is a database of thousands of different proteins that were 3D scanned and then made available online for people to download to their computers, to visualize for their own purposes, and to learn from. So if you actually look up protein database, you can look that up, and we may have potential future workshop opportunities on how to get the files from that database into 3D printed form. But that's where these came from, and what we've done is we've actually gone through the process of downloading those files, converting them, and scaling them so that they're the correct size so that I have a molecule that fits in my hand rather than something that's the size of a molecule. So you can pass this one around. This is a model of an antibody right there. I like that model because it sort of shows the structure of it, why we always represent an antibody in biology textbooks as the letter Y. It's because it's shaped like that. Another one that I want to show everybody is a potassium channel. So this one's great because it's part of our lesson plan on protein structure that's actually meant to supplement the 700X course, if you've heard of that, the MIT OpenCourseWare biology course. This one's great though because it will actually show you, it's part of a lesson plan on protein structure. So it goes through primary all the way to quaternary structure of proteins, and we have different models to illustrate the different concepts. For secondary structure, for example, we have ribbon models that show you the helices, pleats, and everything, those features. And this is a model to actually show the quaternary structure of a protein. So if you look closely at it, you'll see that it's actually 4 proteins fit together, 4 subunits that fit together to create this final thing. And you can actually look down the center of it and see where the potassium ions pass through. So you can pass that around. And this is a newer project that we've actually developed through our internship program. And it's actually a model of a working prosthetic hand. So it's a very simplified model. There's a lot of people that have done a little bit more robust job of it. But this one's actually meant to just take advantage of everyday items that we have available to us. All I really used for this were rubber bands, a couple strings, a couple Velcro straps that I had lying around, and it's actually a functioning part that if you strap this to a wrist and articulated it, you'll be able to move the fingers. And this actually goes along with a lesson plan that starts off the students thinking about where are the muscles in the hand, what actually causes the motion, and how do we sort of extrapolate that through the design process to create something that somebody without a hand could actually use to pick up an object again, grab a ball, or anything like that. So this is meant to really get through the design process and apply it to a real-life situation. And we have a lesson plan for this so that we can actually show our students step by step how something like this is made. And it's meant to be sort of organized in a way where the student always ends up with a product very similar to this, but they also have room to expand. For example, you can see on this one, all the fingers are 1 unit. For each finger, it's just 1 unit. But there's definitely room for improvement where you could have multiple moving fingers on this. So you can pass that around. So those are a couple classroom examples. As I mentioned, there's quite a few more. These are more biology and engineering based, but we're also working on lesson plans that are sort of the central theme is they're around the Common Core standards and next generation science standards. At this point, just about done with my presentation, so if anybody has any questions, I'll be here for a little while.